And it is actually the trade war in between Procter and Gamble that produces Pampers, and other is Kimberly Clark that produces Huggies. So initially, the product was introduced in the market by Procter and Gamble, but later on, Huggies overcome uh, the Procter and Gamble. So this case has been written from the perspective of Procter and Gamble, and Procter and Gamble has reached to the market leader position through a lot of research. So, what was the objective? Procter and Gamble needs to continue and address what customers or consumers are searching in a baby diaper. Right? So, this is the thing. So, for that purpose, um, Procter and Gamble marketing department wants to formulate new approaches to the construction and marketing of Pampers. Right? And since consumer opinion is very important, and here consumers are the toddlers, infants, so they have surveyed the mothers of those infants who are the actual decision maker or who are the customer. And how the case goes. Each mother was given a randomly selected brand of diaper and asked to rate the diaper on the 9 attributes. These are the 9 attributes: X1, X2, X9. And on a extended Likert scale, and overall preference was also taken. The overall preference was noted down, as well as the preference on the 9 attribute. So there are actually 10 variables. One is the overall preference, and other are the 9 diaper attributes. And what was the goal? Um, the goal of the study to learn which attribute of the diaper was most important in influencing purchase preferences. So we are dealing with this aspect only. We are not covering the second part that is related to exploratory factor analysis. So at present we are discussing this aspect. So here on one side we have overall preference, on the other side we have these 9 diaper attributes. So let me take up the case, um, and through this case I am explaining the concept. So I am changing it to my whiteboard or the PPT. Class PPT is there?
Yes, sir, it has come.
Okay. So here on one side we have overall preference of the diaper, and on the other side there are 9 diaper attributes. The names are there. So let us denote the overall preference as Y, and these 9 diaper attributes are denoted by X1, X2, 9, X9. So what was the objective? The objective is to examine that whether these 9 diaper attributes as a whole, or some diaper, or some particular diaper attributes may have some impact on Y. So a type of associative relationship is to be examined. And as you see, the direction of the relationship is unidirectional. So we are examining a dependence relationship. I mean, it has been supposed that this Y is a function of these 9 diaper attributes. Right? And if we further go, this Y is on a scale. This is a scale variable. So this is metric in nature. And these 9 diaper attributes are also on a scale, extended Likert scale. So this is also a metric variable, right? And this type of relationship, this type of associative dependence relationship, where we have a number of the attributes on one side and overall preference on the other side, may be expressed as regression analysis or linear regression analysis, right? And technically, this x1, x2, xn, in generic, they are known as independent variables. And if we use the terminology independent variable, the overall preference is known as dependent variable. It can also be said as predictors, and here it is known as predicted or response variable. They are known as explanatory variables, and this is also known as target variable. So a number of terms can be used so to decide that. And this type of relationship that we are examining is known as regression analysis, right? Now, we know that this y is dependent upon these, may be dependent upon these 6, 9 diaper attributes, and it might be possible that it may be dependent upon something else which is not being covered here. So we are introducing one more term, that is epsilon, right? Epsilon is known as error term. Error doesn't mean something went wrong. Error means extraneous term or residual or noise. So y is a function of these. And if the nature of this function is linear, this is known as linear regression analysis. So we are going to study this topic, right? So we are considering one-way associative relationship where we have a single dependent variable, and on the other side we have one or more than one independent variable. Moreover, all the variables used here are metric in nature, right? They are measurable in nature, right? So this is the subject matter of a very popular, a very famous modeling technique that is known as linear regression analysis. So any question up to this point? Any question up to this point? Okay. So as I have mentioned, we are examining dependence associative relationship between a single dependent variable and single or multiple independent variables. If there are only two variables, one y and one x, that is known as bivariate regression. Otherwise, this is known as multiple regression. So bivariate regression is a particular form of multivariate or multiple regression, and we are studying this. Then obviously the bivariate regression would be covered. So data must be metric in nature. Now the purpose of analysis is number one, prediction. We want to predict y as a function of x1, x2, xn. And the other one is we want to know which of the explanatory variable or which of the diaper attributes are having higher amount of impact, and so on. And this is the proposed model y. So this can be written as y equals to beta 0 plus beta 1 x1 up to beta 9 x9 plus epsilon, right? So this model is known as population regression model or population regression equation. And what is our objective? Our objective is to estimate these betas, which are known as regression coefficients. And for that purpose, we are using a sample because we don't have the access to the complete population data. So the sample linear regression equation, linear regression model, can be expressed as y is equal to b0 plus b1 x1 up to b9 x9. We cannot estimate epsilon. So before moving forward, let me explain this. Here, they are being estimated and they are from the sample, means from beta 0 to beta 9 x9. So since they are known, so this part is known as deterministic. But this epsilon is outside the model. This epsilon is outside the model, so cannot be estimated. Since it cannot be estimated, so it behaves like a random variable. So epsilon is a random variable. Now, this y is a combination of deterministic variable and a random variable. So y in itself is a random variable. So random variable means we cannot estimate the exact value of y. We can only estimate the average value or expected value of y. That's why this regression is also known as average regression. Let me cover the next slide, then I will be taking the questions. So here, epsilon, since epsilon is stochastic means random, right? This is random. While random variable is non-stochastic, they are deterministic, they are known, right? So y in itself is also random. And one more thing, very important thing, this linearity is with respect to regression coefficient, not with respect to independent variable. What does this mean? If we write these two equations, then obviously there is no doubt this is a linear regression. And if we write y is equal to beta 0 plus beta 1 x1 plus beta 2 x1 square, and this is equation 1, this is equation 2, equation 3 is y is equal to beta 0 plus beta 1 square into x1, right? So here, the second equation is linear with respect to regression coefficient. Here, y and beta 0, beta 1, beta 2 all are in a linear degree. So this will be a linear regression. But here, beta is in the form of square. So this is not linearity with respect to regression coefficient. So this is non-linear. So it is very important, right, that we should recognize which one is linear or which one is not linear. Let us take one more example. Y is equal to beta 0 plus beta 1 into log of x. And another equation, y is equal to beta 0 plus x into log of beta 1, right? So the first equation, if we look for the first equation, this is linear with respect to regression coefficient. Both are having single degree, right? And in the second equation, it is not linear with respect to regression coefficient. So this is linear and this is non-linear. Okay. So up to this, is it clear or any question? Up to this point, is it clear or any question? Is it okay? Okay, right. Now, since epsilon is there and epsilon is a random variable, so this is a statistical relationship, not a mathematical or functional relationship. And because of the presence of epsilon, only the average value of y can be estimated. And one more very important thing is regression model do not establish the causal relationship. It establishes only the associative relationship. That may be caused, that may not be caused. It establishes only the associative relationship, right? So it actually provides only the necessary condition, but not the sufficient condition. That's why in order to establish causal relation, we go for experimental research design. Okay. So we never say that regression analysis is a cause and effect relationship. It is just the study of associative relationship. Conceptually, these points are very important. Otherwise, if you run the analysis and write in the research paper, there may be objection if you use it as a causal relationship or you got confused with the linearity or the other aspects. So, is it okay? or any question? Okay. So now, uh, what is the object? First is the objective of multiple regression. Right? Objective is um, appropriateness of the research problem. Right? These things are being discussed. This is the first step. Right? Here, I have already explained there are two objectives. One is the prediction, where we try to predict the value of y. Normally, in analytics or in data science or in machine learning, we are more interested in the prediction, but the other aspect is the explanation, which examine regression coefficient to establish a theoretical reasons, right? We through this we can establish that these factors are affecting the y, so there must be a theoretical reason. So it is used for the theoretical purpose, means it is used for our research purpose, for research papers, as well as for marketing research also. So these 2 points are very well related, having some difference to the domain where it is being used. And it is again being reiterated that this is a statistical relationship, not a functional relationship. Now, selection of the dependent variable and independent variable, very important for all the researchers, that there should be some strong theory behind that, right? Means whatever variable you are taking, it should have a support of literature review. Literature review may be in the form of research paper, maybe form of in previous study, maybe form of some white paper, and so on. So unnecessary, we shouldn't include the irrelevant random variables. Now, related to the sample size, this is a large sample problem. So what are the thumb rules? It should be 5:1. Means for each predictor, there should be 5 cases. So here we have 9 predictors. So the must sample size is 45. But for a better analysis, the ratio is 20:1. So our sample size should be more than 180. We are already having a sample size of 300. So this is okay. Right? These concepts I will be taking later on. Now I am running the analysis and then we will be discussing. So any question up to this point, or we should run the analysis through SPSS? Any question? Okay. This case I have already shared. This is the case Pampas data. This is our y variable and these are our diaper attributes. So we go to analyze, then we go to regression, and then we go to linear regression. Okay, so our path would be analyze, then regression to the linear regression. Only one dependent variable may be there. For more than one dependent variable, either we can try canonical correlation or structure equation modeling. That will be covered later on. So this is why. Now, since we are running it for the first time or discussing it for the first time, I'm entering all the variables in one go. All the variables are being entered simultaneously. So this method is known as enter, where all the variables are being entered in one go. There are other methods also. We can enter one by one, that is known as forward method. We can enter the variable in different steps, that is known as stepwise method. And backward method means we can remove variables one by one. And remove method is we can remove a group of variable that are not contributing in one go, right? So anyway, this is the most common form. And since we are running it for the first time, so that is known as a method that is being used as enter. Right? Now we develop certain button like statistics. Obviously, regression coefficient is there, model fit is there. We can use R square change whenever we are running forward method, backward method, remove method, or we are running stepwise method. Anyway, Since we are having only one model, so there won't be any R square change. So we are not taking R square change. Then we can have descriptive. Then we have part and partial correlation. This I will be discussing why I am taking this. We can have collinearity diagnostic also. This is also used to examine some assumptions. We also include Durbin-Watson, which is used to examine some other type of assumption that is known as autocorrelation. Right? And these things are being entered. Then we press continue. Then we go to the plots. So here we entered Z residual. Z residual means standardized residual in the y-axis and Z predicted in the x-axis. Right? I will be explaining what do we mean by residual and what do we mean by predicted. And for the normality checking, I am taking histogram as well as normal probability plots. We continue. Right? Then save is not required, but the just for the teaching purpose, I am saving predicted value as well as residual value. Though this is not required for the normal study, but just for the demonstration purpose, I am taking standardized predicted value, unstandardized predicted value, and unstandardized residual also. I will be explaining what they mean. Right? Option is not required. Already things are there. Then we press OK. So we will be having output. I am saving the output. This output is so. Any question up to this point? Yes, any question? Okay. Now we will be discussing this output, right? So for that purpose, let us go back to the PPT and we will be discussing. Let me have one more. Now we are discussing steps in the regression analysis on this whiteboard. Remember, this is a study of associative relationship. So it is just like examining the relationship, and all the steps that are there when we examine the relationship between two human or relationship between anything. So whether you think in a practical sense or you think in a statistical sense, steps remain the same. So suppose um, someone has asked you to examine the relationship between two people. So the first question that we need to answer is whether there is relationship or not. Obviously, if answer is yes, then we will be moving forward. Otherwise, we are not moving forward in this direction. So statistically, this is known as examining. Since here relationship is being expressed by the regression model, so here we say examining the significance of regression model. So this is the first step. Now, there may be two answers, no, or there may be yes. If no, then analysis stop. If yes, then we goes forward. Then we go forward. So the second thing that we examine is related to the type of relationship or strength of the relationship. Like we are friend with with more than one person, but it is not necessary that both are equally good or both are equally good bad friends, right? Some may be very close, some may not be very close, right? So we examine strength of the relationship. So technically this is known as examining the strength or predictive accuracy, because this model is used for prediction purpose, predictive accuracy of the regression model. So this is the next step. It will be there only if we get the answer yes from the next. Here we never say that for relationship we require everything should match, right? There may be two or three reasons that defines the relationship. So here, so this happened here also. We are considering 9 diaper attributes. So it might be possible that all 9 diaper attributes are affecting overall satisfaction. It might also be possible that only a few of 9 are having impact on uh, relationship. So we examine what are the defining factors for the relationship. Technically, this is known as examining what are the significant predictors. Now, if there are only one, then we don't bother, we consider that only. But if we have more than one, three, four, five, so we want to know which is the main reason, right? So the next step is creating hierarchy of factors for the relationship, or we can say creating hierarchy of significant predictors. Means only those predictors that comes out to be significant are put in the hierarchy, which one is at the top and which one at the bottom and so on. And the last step is, this happens in our real life also. We normally say that all childhood friends are the real friends, right? The friendship that is being built on money and built on um, some um, convenience may not go for a long term. Yeah, or we say that office friends are not the real friends. Our student friends are the real friends. So how we made this statement? These statements are being made as per our experience from our neighborhood. Means we study a neighborhood which is technically known as sample. So we study a sample around us, and from that sample we develop the world view. So this concept in statistics is known as developing or proposing the regression model. So the model is just a generalization of the things that are there. So we are at the last step, we are proposing the relationship model or proposing the regression model. Right? Now, there is one more step that I haven't said. Let us put that at the 0th state. This is known as assumptions checking. Why this is so important, that will be discussed later on, right? Assumptions checking for the proposed model. Okay, so this step we will be discussing later on, that why this assumption checking is very important. So any question up to this point, or is it okay? Any question? Okay, right? So we will be discussing all these aspects in one go. So we are checking assumption in the last for a defined purpose. So the first step that we are going to discuss here. Now, I am only taking uh, the technical words. I am not taking the real life words, because I am just connecting the statistical analysis with the real life that I have already connected. But for the writing purpose, we will be discussing the technical part. So first is examining significance of the regression model. So here we take H naught. Remember what was the rule for H naught? H naught is used to be nullify. H naught is, it assumes no relationship, no difference. So H naught proposes that the proposed regression model is insignificant. Means the proposed regression model is zero. Now what does this mean? It means all the betas, all the regression coefficients are zero, and R square. I will be introducing R square in a short while. They will be zero. So this is the regression model is insignificant. We examine whether it is there or not. Right? So for that purpose, I am showing you the data sheet, and through that data sheet, we will be discussing the concept. So I'm showing you the data sheet. Then I will be coming back. So this is the data sheet. Now, if we observe this preference or y, one value is 5, one value is 7, one value is 1, one value is 6, 3, 2. Right? So we say some values are high, some values are middle, some values are low. So we can say that there is a variation. So this is known as total variation. So we say that there is a total variation in the dependent variable y. Now, the question, now we examine what are the reasons, what are the factors for this variation in y. So one reason may be that suppose some person wants to buy diaper because of the attribute absorbency, and if proper absorbency is there, that person will give high score, and if proper absorbency is not there, that person may not give such a high score. In the same way, suppose some mother buy a diaper because of count and price. So if count and price are reasonable, that mother will be giving high score uh, to y. Otherwise, it will be giving low score to y. Means one reason of this variation in y is because of these factors, that is known as because of the regression model. So this type of variation is known as explained variation because it has been explained through the model. But with our all efforts, right? How many predictors we take? There are some other predictors also which are not including in the model, and they may have impact upon the preference. Like here, suppose some advertisement is there. So because of advertisement, preference may increase. Suppose um, it is a winterish season, and it is a winterish season or it is a rainy season. So in the rainy season, mother wants higher number of diapers for their kids, right? Or there may be some public opinion, there may be some peer recommendation, right? So sometimes the preference increases and preference decreases as well, as because of peer recommendation. So the preference may be affected by the variables that are there in the model. It may be affected by the variable outside the model. So that is, the first one is known as explained variation, and other one is known as unexplained variation. So this I am noting down here. So to explain the concept, just a moment. So here we examine total variation. So we are examining total variation in y in the dependent variable. So one reason can be explained variation. This explained variation is because of the predictors that we have taken. So this is known as variation because of regression. And another type of variation is outside the model. So that is known as unexplained variation. This is known as because of something else that is known as residual or the error, right? So now, suppose explained variation is high. Explained variation is high means most of the variation is because of the regression model. So if this is the situation, then we can say that our regression model is there, means regression model is significant. And if there is opposite of the case, means explained variation is low, unexplained variation is high, means our model cannot capture the real reason for the variation. So in that case, we say that our regression model is insignificant. Right? Now, we convert them in a ratio that is known as F ratio. So F ratio is explained variation, means variation because of regression, and unexplained variation. Is variation because of residual. Now, suppose explained variation is very high. So numerator is very high as compared to denominator. So value of F would be much higher than 1. And now F is an statistic, and this is the distribution of this statistic F. It can never be 0, right? And suppose F is very high. Since F is very high, so it will lie towards the right side. And correspondingly, the right tail probability is known as p-value. Right? So if F is very high, F is very high, it indicates that p-value significance F would be low. And if this significance F is less than 0.05, we say that we reject H0 at 5% level. So rejection of H0 means we are rejecting insignificance. So we say that our model is significant. Right? Now all this discussion has been done through the variation. So this is there in a table that is known as ANOVA. Right? I will be showing you the output. So any question related to this concept? Is it okay? Any question? Yes, class, any question?
No, sir.
Okay. So now I am showing you this part. We will be discussing this ANOVA. Other tables will be discussed later on. As you see here, this is the total variation, and the two parts are regression, which is the explained variation, and the residual. The magnitude of explained variation or variation because of regression is 93, and the magnitude of unexplained variation or residual variation is 1.071, very low as compared to the explained variation. F is the ratio of explained upon unexplained, or F is the ratio of regression and the residual. So if we divide 93.491 by 1.071, we will be getting 87. Now 87 is a big value, right? So correspondingly, the p-value or significance is 0.000, which is less than 0.05. So here I am writing down this on whiteboard just for your reference. So from ANOVA table, I will be showing you later on. From ANOVA table, what we get, that significance is 0.000. There is no number up to the 3 places after the decimal. So obviously it would be less than 0.05. So we reject H naught. And what does reject H naught means? It means our proposed regression model is significant. I will be showing you the slide later on. Our proposed regression model is significant. Means it gives us a green signal to go forward. Means these 9 diaper attributes as suggested by the Procter & Gamble marketing department have significant impact on Y. Right? So this is the analysis. So hopefully this is clear to all of you. Now, just have a photograph of this table also. That is a model summary. Model summary. Next table, we will be discussing this. This is a model summary. So photograph done, screenshot done. Okay. Now we are discussing the second aspect. The second point. What was the second point? Let me change the thing. The second point is examining strength or predictive accuracy, means how much accurate our model is of the regression model. Now it is being done by a term that is known as R square. It can be written as R square or R square. This R square is the ratio of explained variation or sum of square. Sum of square is just the numerator divided by total variation or sum of square. Right. Now, this explained variation is always a part of the total variation. So explained variation can never be greater than total variation. At most, explained variation can be equals to the total variation. Right? So this R square can never be greater than 1. And this is a variation. This is a sum of square. Any square can never be negative. So the minimum value is 0. So value of R square lies in between 0 and 1. Now, let us discuss a value. Suppose this R square is 0.90. So 0.90 is being written as 90 upon 100. And if we compare with the formula, what we get? What does it indicate? That our model is able to explain 90% of the variation in the Y. Right? Remember the value is 0.90. 0.90 can be written as 90 upon 100. Right? So we can, how can it be interpreted? If we compare with the formula of R square, we can say that our model is able to explain 90% of the variation, or our model is having 90% of the variation. Right? So is that okay? Whiteboard is okay, class?
Yes, sir.
Now, as per the output, what is R square? This you have in your photograph, that is 0.73. It means this is 73%. So we can say that our model is able to explain 73% variation in Y, or our model contributes to 73% variation in the dependent variable. So obviously this is a high value. So we can say that our model is strong. It means if R square value is near to 1, we say that our model is strong. Right? And suppose R square is 0.15. It means our model is able to explain only 15% of the variation. It means the remaining 85% of the variation is being explained by outside the model. So in that case, we say that our model is weak. Right? So if the value of r square is near to 0, we say that our model is weak. So r square is clear? Yes, class? R square is clear? Okay. Now, if we are getting point 0.2, okay, now there is no clear cut demarcation which value should be written as high and which value should be written as low. It actually depends upon the subjectivity of the researcher. That's why in the research paper we always explain r square as our model is able to explain 30% of the variation, 40% of the variation, 80% of the variation, or 90% of the variation. Right? In a number of researches, like not only in behavioral science, uh, actually in the field of the commerce and the economics, even a low value like point 0.2 or point 0.3, we say that our model is substantially um, strong, right? So it is always better to avoid the judgmental word like strong or weak. We can always say that our model is able to explain this much percent of the variation, or we can say that our model has predictive accuracy of, or we can say our model has a predictive accuracy of 73%, right? And if we code that, so we transfer the onus to the other person, whether the other person is ready for 73% or other person wants a higher value or even accept the lower value, right? So that's why I have explained r square in the form of percentage of the explained variation. Is that okay, Sebastian? Is that okay? Right? So it is always better to write uh, in the form of technical language instead of using the judgmental word. Right? Now, we have discussed r square. Now, actually, r square has some weaknesses. So, now this r square has certain weaknesses. This r square depends upon number one, size of the sample, that is n. Right? If n is low, if we have a small sample size, then r square would be inflated, r square would be high. Number two, it also depends upon number of predictors or number of independent variables, that is k. And here concept is, if k is large, then r square got inflated. So what we do? In order to improve r square, this r square is normalized with respect to size of sample n and number of predictors. Or it is also said to be r square is adjusted with respect to n and k. And correspondingly, we have another coefficient, that is adjusted r square. Right? In economics and commerce, it is also being written as r bar square. So this r bar square is actually r square 1 minus r square into k divided by n minus k minus 1. You can ignore the formula. But here we are adjusting r square, right? So obviously it means if there is a large difference between r square and adjusted r square, it is better to interpret adjusted r square. But if there is not much of the difference, it is immaterial whether we use r square or adjusted r square. Like in our case, in our case, as per model summary, table. It is the output model summary table or output. Adjusted R square is, just a moment. Adjusted R square is 0.722, right? Remember, adjusted R square would always be less than or equals to R square, right? So R square is 0.730, adjusted R square is 0.722, no substantial difference. So whether you interpret 73% or you interpret 72%, there won't be any much of the difference. But if there is a big difference, one value is 0.80, other value is 0.60, obviously you should interpret adjusted R square, right? So this is the interpretation of strength of the model. So any question up to this point? Or is it okay? Any question up to this point? Okay. Now we are moving further forward. So we have covered the two steps. Now the third step is point number 2. Whole of the point number 2. Okay. Right? So here we examine strength of the predictive accuracy of the regression model. It is done by the R square. R square is the ratio of explained variation of sum of square divided by total variation of sum of square. The value of R square lies in between 0 and 1. And if values are near to 1, it is being said as that our model is strong. And if the values are near to 0, we can say that our model is weak or having low predictive accuracy. But it is better to use in the objective form and not the judgmental subjective form. Like in our case, R square is 0.73, right? 0.73 means our model is able to explain 73% of the variation. Let the other person decide whether that person wants to say 73% as strong, very strong, or moderately strong. Point number 2 of the dependence. Okay. And related to this R square actually depends upon two values, two things. Size of the sample. If we have a small size, right, then there will be always a better fitting. And this better fitting is not because of the relationship, it is because of the mathematics, right? So if sample size is low, then R square will automatically got increased or R square got inflated, right? So one is N. N is the size of the sample. Second thing is number of predictors, means how many predictors are there. Since R square is the ratio of the explained variation, if and variation is the sum of square. So sum of square can never be negative. So instead of 9, if we take 21 predictor, then all predictor will contribute even to a minor amount, but that will be a positive. So the numerator will always increase. It will never decrease. Since the numerator will always increase, so with increase of predictor, R square would increase. So that's why we normalize R square with respect to size of the sample and number of predictors. And accordingly, we define adjusted R square. So this is the adjustment factor. So if there is a big difference between R square and adjusted R square, it is better to interpret adjusted R square. Otherwise, it is immaterial whether you interpret R square or adjusted R square. Is it okay, Ms. Tanu? Okay. Now, the third point is...
Hello, sir. This is Dr. Noor here. I have a question.
Yes, ask.
So, sir, actually, as you have very lucidly explained R square and R, but I have a one dot actually, because most of the time, as you mentioned that if R square is good, then we should define it that the model is appropriate or not. It is
No,
up to us.
no, no. There is whether model is significant or not. First thing is significance, right?
Yeah.
Right? Which simply tell
So
whether
my
there is
question, actually,
existence
sir,
of
my
one
question
moment,
is,
one moment, existence of
most
the model. Yes.
Actually, sir, most of the time what happens, like in some of the model R square is sometimes it is 0.10 or 0.20. So generally in that case, we used to shuffle the model, and sometimes we are incorporating more variables, more independent variables to better to make it more appropriate. But my question is statistically, if for example R square is lesser, so can we go with the same R square, substantiating with the earlier
Yes.
existing research
Okay.
that we have seen a number of researches where R square is lesser, but still they are going ahead with that. So is
Okay.
it possible to go with
Okay.
the
Okay,
lesser R
Nurul.
square?
Okay, Nurul. Actually, there are two objectives. Number one is the prediction, right? If we go with the prediction, we obviously require high predictive accuracy, right? So if we go with the machine learning part or data science part, then obviously R square should be high, right? Otherwise, there will be an issue on the accuracy. But related to the research, obviously, if R square is not so high, but model is significant and appropriate variables, appropriate predictors comes out to be significant, we can go with that low R square also. There are n number of reasons for R square to be low. What are the reasons? Suppose the model is not strictly linear and we are using it as a linear analysis. So it gives us indication that something may be improved, right? And obviously, if we increase number of predictors, R square will always increase. So that's why we interpret adjusted R square. And there is no point of unnecessarily increasing R square, right? But we try to have better R square whenever we try to predict something, because that requires higher amount of the predictive accuracy. But our purpose is explanation, then even low R square can also be accommodated.
Okay, sir, thank you very much for this. But sir, may I know, like sometimes, many of the times we have seen that in a model, like even after incorporating more variables which we can accommodate, R square is not that much improved. So
Obviously,
how statistically we can justify this, that by putting all sort of model which can be incorporated, R square is little lesser. So how statistically we can justify this point, sir? Can you please just shed light on it?
okay, two things. If on addition of additional variable R square is not increasing, it means additional variables are not contributing to the model. One point. Second, suppose the type of relationship is not strictly linear. It is log linear in nature. So even if you add R square, so there an issue of the bias, means the type of relationship that is actually exists has not been covered. So this is one of the reason. Second, if you support proper literature review, means a predictor is taken because that has a support of literature review, obviously that research paper may be accepted, right? But if you are going strictly with the empirical analysis, means there is no support of R square and no support of the literature review, then it is expected. Otherwise, a reviewer can always put a question that here R square is quite low. Quite low means you have missed certain predictors or you have missed the exact form of the relationship. Is that okay?
Yes, it's a very much okay, but sorry for one more question, sir, related to it actually. For example, if I am going to do a new kind of research where I've been developing a new model, okay, sir. And while hello, whatsoever factors I think the predictors can better represent it, I have put all the predictors in the model, but still, if R square is lesser, and I'm not having that much of backup because it is a new core of area, new area where not that much research has been conducted. So in this particular situation, what should we do? Should we go with the same model, assuming that it is better representing the entire thing, or we
Okay.
should quit that?
Yeah.
What do you suggest in this particular specific?
Okay, so in that case, you should also try to see that is the third point, that what are the significant predictors, whether that are making sense or not, and you have to check the assumptions also, right? Whether assumptions are being followed or not, because in a number of situations, assumptions can play a bad role also related to the model. Is that okay?
Okay, sir. Thank you, sir.
Okay. And there was a question, sir, why we are using hat in the equation while we explain. Okay. Actually, there is a convention Normally we use capital letters so to denote the population things, or we can use Greek letters so to denote the population thing. But when we come to the sample, we can use small case results letters, we can use Roman letters, or we can also put hat also. So hat represent the predict that is a estimate thing from a sample. So this is a reason that whenever we put hat, hat simply shows that this value is from the sample. That is not a population thing. Okay, Mr. Anirudh?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes. Okay, right. So now we are coming to the third point. Here we are examining. And one more thing, since a lot of discussion is there, regression analysis is an empirical technique. So whenever you have to establish some theory, then it is better to go for structural equation modeling, because that is a confirmatory theory. In regression analysis, we go from we go through the empirical way. From data, we derive the theory. While in the structural equation modeling, we confirm the theory through the data. So they are the opposite in nature. So if there are some theory and that theory is to be confirmed, it is better to use structural equation modeling. And if you are developing the model, right? If you are empirically establishing something, then regression analysis is being recommended. Right? So this is the additional point of importance whenever we go for the research papers. Right? Okay, so we will be discussing the third point, that is known as examining the significance of the predictor. Just to establish the concept, I am taking an example of bivariate regression. Suppose this is a bivariate regression model, y is equal to beta 0 plus beta 1 x. Right? If we compare it with the line, regression line, so this is parallel to y is equal to mx plus c. Right? So this beta 0 is the intercept or the constant term equivalent to c, and this beta 1 is equivalent to m. So this beta 1 is known as regression coefficient, which is parallel to m. Right? So which is parallel to m. And remember what is the m? M is the slope. So m can be written as delta y over delta x. So this beta 1 can be written as delta y over delta x. So what does it provide? It provides rate of change in y with respect to x. And if we put delta x equals to 1, this beta 1 becomes equals to delta y. So it means the change in y for unit change in x, right? So this is the role of regression coefficient, right? Let me generalize this. Now our model is a multiple linear regression model. So y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 and so on. Now this beta 1 is known as partial regression coefficient. Remember earlier we put the name as regression coefficient. Now we are putting partial regression coefficient. Why partial regression coefficient? Because now it has been interpreted as, because earlier we have a single variable. So we comment only on x. But here we have more than one variable. So now we interpret this as rate of change in y with respect to x1 provided other predictors remains constant. That's why this is known as partial regression coefficient. Right? Now, suppose in any of these two cases, whether the first case or the second case, if beta 1 is 0. Beta 1 is 0 means rate of change is 0. Rate of change 0 means that predictor is not having any impact on y, right? So here it is being examined here. So in this case, we examine h naught as beta equals to 0 versus beta is not equals to 0. If beta is 0, we say that the corresponding predictor, corresponding independent variable is inconsequential, is insignificant. And here we say that the corresponding predictor is significant. Okay, so we examine this beta equals to 0 or not. This is done by t-test, which is equals to beta cap divided by standard error of beta. You can ignore the formula. It follow t distribution. And if the p-value, significance of t is less than 0.05, we say that we reject H naught at 5%. So rejection of H naught means beta is not 0. It means beta is not 0. That is, the predictor is significant. Is that okay? Right? I will be showing you the table. Is that okay, class?
Yes, sir.
Okay. Right? So now I am sharing this part through the output and we will be discussing. Have a screenshot of this. This is the coefficient. Have a screenshot of this. The coefficient part. Done? Okay. So now here, if we look, these are the regression coefficient. These are the beta values and these are the p values. Now here what we see, constant is significant, constant can be ignored. Count per box is having p-value less than 0.05. Count per box is significant. Price is not significant because it has a higher value, higher p-value. Value is not significant. Unisex versus separate sex is significant because it is having p-value less than 0.05. Style is insignificant. Absorbency is having a p-value of 0.031. It is significant. Leakage, comfort, and tapping are not significant. So here we have three significant predictors: count per box, unisex versus separate sex, and the absorbency. Is it okay? I will be writing down on the whiteboard. Is it okay, class? Right. So I am writing down this output on the whiteboard. So here we check that what are the significant predictors? Significant predictors for the diaper preference is count per box because its p-value is 0.000 less than 0.05. The second one is unisex versus separate sex. Which is having significance value 0.000 less than 0.05. And the third one is absorbency, which is having p-value as 0.031. So these three are the significant predictors. Now, class, as a researcher, any point of concern in this output, you can unmute and answer. any point of concern with this output? Or no? Okay, let me put in another words. Here we have a big F value. We have significant ANOVA. R square is relatively very high. 73% is very high as for the market research problem. But only 3 of the 9 predictors comes out to be significant, right? Means only 33% of the predictors comes out to be significant. So this should put a question mark on our output. Further, if we see to these predictors count per box, unisex, and absorbency. So, as a common man, some important predictors that should be there are being missed, like leakage, comfort, price, right? So, it means with this output, there should be a warning bell to all the researcher, all the people who know a bit of the statistics or the research. Is that okay? Right? Remember, we haven't done anything wrong, right? It is being done by one of the best software, that is SPSS. But even then, this output is a bit of concern. Is that okay? Can you appreciate um, uh, this critique of the output, right? So there must be some reason. So once you catch that there is some reason behind that, then obviously you will try to search what that reason will be. That will be discussed later on. Anyway, we are still moving with this output. Remember, we have done up to 3. Means in order to ensure the preference of the diaper, we should work on number 1, count. Number 2, unisex versus separate sex, right? Means that is related to the style element. And the third one is the absorbency element. Now we are considering the hierarchy. Means among these 3 predictors, what are the number 1 and so on. So this is the 4th point that we are going to discuss. 4th aspect we are going to discuss. Hierarchy of significant predictors. Now we have 2 type of regression coefficient. One is beta, that is known as standardized regression coefficient, right? Means it is independent of scale, origin, or unit of the measurement. Another is B. B is known as unstandardized regression coefficient, which is in the actual unit, actual scale. Now let us take 3 predictors, x1, x2, x3. x1 is on a scale of 1 to 5, x2 is on a scale of 1 to 10, x3 is on a scale of 1 to 100. Right? And here all the b values are 5, 5, 5. So if we look for only the b values, it appears all the 3 predictors x1, x2, x3 are equivalent because they are showing the high value. They are showing the same value. But if we consider the scale also, here this 5 is a high value because it is towards the highest point. This 5 is a middle value, so this is moderate. And this 5 is a low value, right? So in order to create hierarchy, we consider only beta. So hierarchy of significant predictors is being created by considering absolute value, means ignoring sign of beta. Why absolute value? Why we ignore the sign? Because plus denotes the direct relationship. If one increases, other also increase, means the change is in the same direction. And the minus sign represent the inverse relationship. means they go in the opposite direction. But here we are concerned with the relationship. We are not concerned with the direction. So it is immaterial whether the value is plus or value of minus. If value is high, it will be treated as a high. So hierarchy of significant predictor is being created by considering the absolute value of beta, right? So let me write the beta value as from the table that I shared, that I asked you to have a screenshot. So here I'm writing down the beta values of these three significant predictors. So count per box beta value is, let me write it from the output, 0.269, the positive value. The second one is unisex versus separate sex. So its beta value is 0.362. And beta value of absorbency is 0.204. So now let us have the hierarchy. At the first position, we have unisex versus separate sex, which is a style element only, a fashion element. At the second position, we have count per box, right? And at the third position, this. Okay? Right? So now, is it okay or any question? Is it okay or any question up to this point? Yes, class? Okay. Now, the question from my side. This product is a very common product. All of us know. Lot of advertisement is there also. It is a baby diaper. So the analysis says that the most important predictor is unisex versus separate sex, which is actually a fashion element or a style element. Even in these three significant predictors, it appears that the most important predictor should be absorbency. Mothers would be more interested in absorbency for their kids as compared to the fashion element. So don't you think this output is a bit of concern? Hello, don't you think so? Yes, right. So as a researcher, that's why the role of the domain knowledge comes. So this domain knowledge tells us that there is some issue in the output. Okay. Now, what is the issue? Remember, deliberately, I haven't interpreted this point. That was assumptions checking. Deliberately, just to establish the importance of the assumptions for any analysis. So had I checked it earlier, so we could have caught that there is some issue in the data, right? So we haven't done the assumption checking. Now, why assumption checking is important? Because we are using a particular type of regression that is known as ordinary least square estimation, right? So for that purpose, I am showing you this very important slide that we ignored, right? This is the assumption checking. The number one is the linearity. This is already there, right? This is independent variable is known, it is there. Now, there is an assumption that there should not be high correlation among independent variable, right? This problem is known as multicolority, right? Now here I am discussing multicolority, right? We say this is a rule, not exception. So we say, as an econometrician, we say that multicolority is a rule, not exception. Means multicolority will always be there. So we are not concerned with the presence or absence, we are concerned with the magnitude. And it is a very common problem in cross-sectional data. Means one-time study or the survey data. Now, why this problem occurs? Now, suppose, let us take some other example, some medical example. we want to know about the level of suppose level of COVID mm, infection. So why is the level of COVID infection? Suppose we consider only one variable x1 here. Suppose this x1 is fever, right? If we take only one variable x1, so there is some issue that this x1 may not exactly measure the presence of COVID, right? So this type of error is known as measurement error, right? So if we take one or two variables, there may be a big issue that the real disease might not be got, right? So this is known as measurement error. Like in our case, right, we have taken absorbency as well as leakage. Why we have taken more than one? Reason being, it is being thought that if only absorbency is being asked, it might be possible that respondent might not catch what does absorbency means or what is the role of the absorbency. In the same way, if we use only the leakage, there will be issue like why not absorbency is there. So in order to cover the measurement error, in order to reduce the measurement error, we consider more than one predictors, more than one variables, right? But all these variable actually measure the same thing, right? So now with increase of variables, measurement error got decrease. But since these variables are measuring the same thing, since these variables are measuring the same thing, so there must be high correlation among these variables. And this problem is known as multicolority, right? Just a moment. Why we are discussing these assumptions? Because we are using classical linear regression model. Here it is being mentioned for least square method, OLS estimation, the method that we are using, that is known as classical linear regression model. So these assumptions that we are discussing belongs to this model, that is the classical linear regression model, which is commonly used by the software. So if these assumptions are being fulfilled, then only we can apply, we can interpret this OLS estimation or classical linear regression model. Anyway, right? So this is the multicolority. So here it is being written as multicolority is a rule, not an exception, right? And and how it happens? Because there is high correlation among variables. And what is the implication? What is the implication? That the variance or standard error of the estimate got inflated, right? So a number of t ratios become underestimated. So what happened overall? We have high F value, high ANOVA value, high R square value, but most of the independent variables becomes insignificant. It is happening in our output. And it is also happening, it is also showing that a number of important predictors are behaving in a different manners, right? Either they become plus or they become minus or they become zero, right? So this is a reason for this. Means there is high correlation among variables that I will be showing you. Means our data is having high multicolority, and because of high multicolority, there are issues. Now, how can we identify? Here we interpret these two things. Right? I am not going in very detail because already more than 1.5 hours has been there. That is variance inflation factor. Right? What is a thumb rule? If VIF is greater than 4, then there is a concern. If VIF is greater than 9, then there are severe multicolority. So there is a problem, right? So we will be interpreting VIF, and we are also interpreting this conditional index. And what is the thumb rule for the conditional index? Right? All these technical details are there. I am not discussing this because we don't have much of the time. If all the conditional indices are less than 10, then low multicolority, which is acceptable. If all the if some values are in between 10 to 25, this is moderate to high. So we may ignore or we may take, and but if any of the conditional indices is greater than 25, then there is a severe multicolority. So you can have a screenshot of this slide. I will be interpreting it through the output. Have a screenshot of this. We are checking the assumptions. Screenshot done. Is it done? Okay.
Yes, sir.
So now I'm showing you this part. Now, if you look for the coefficient table, right, here we are having the correlation. So as you see, correlation coefficient between price charge and the value 0.73, a big value. Correlation coefficient between price charge and the count per box 0.864, big value. Correlation coefficient between style and unisex versus separate sex 0.894, a big value. Correlation coefficient between absorbency and leakage 0.942, a big value, because correlation coefficient is in between -1 to +1. Correlation coefficient between absorbency and comfort 0.731. So there are a number of high correlation values. So it indicates that there may be multicolority. Anyway, we are discussing some better measure. Now, in the coefficient table that you are having a screenshot, you can check that there are two VIF values that are over 9. One is absorbency, other is leakage. So there are two VIF values that are substantially very big. Okay, so it shows that our data is having severe multicolority. We cannot ignore. Further, if we go with the collinearity diagnostic, if we try to see the conditional indices, as you see here, what was the thumb rule? If conditional indices is greater than 25, then we have severe multicolority. There are three dimensions, 8, 9, 10, which are having conditional indices over 25, 29, 41, 46. It means our data is having severe multicolority that cannot be ignored. Right? So this is a reason for this bad output. Right? So we have to do something in order to cover that. Right? Is it okay? Is it okay, class?
Yes, sir.
Okay. Right? So now this assumption, this multicolority is a very common problem with a cross-sectional data, and this is indeed a cross-sectional data, so there are issues. Now we are discussing other assumptions also. Right? So now everything is done correctly, everything is being done by a good software, right? And there is no wrong interpretation. Even then the output that we are getting is not that much good. So let me share. Okay. So this we have discussed. Right? Now we have other assumptions also. What are the other assumptions? That the error term is epsilon term, residual, should follow normal distribution. Number one, it should follow the normal distribution. Right? I will be showing how it can be checked. The second is it will always be there, that the mean of the residual would be 0. It will always be there. The second thing is residuals should be uncorrelated with each other. Right? Otherwise, there is a problem that is known as autocorrelation. So this autocorrelation is a common problem for longitudinal data. Means the secondary data that is being normally used by the commerce people or the economics people have this problem in a much big way, right? It is not that much problem for a cross-sectional data. So otherwise, It is a common problem for the longitudinal data. So this is autocorrelation problem. I will be checking this on the output. The next is all the residual must have the common variance. So common variance is known as homoscedasticity. Otherwise, there is a problem that is known as heteroscedasticity. Right? These assumptions are there in the, so normality is there. The first one is the normality. We will be having histogram of the residual. This we have instructed. So now histogram of the residual is being interpreted whether there is normality or not. Or a normal probability plot, remember this we have discussed on the day one, right? Means all the points should lie very close to 45-degree line. So this is used to checking the normality. After that, autocorrelation, how we check the autocorrelation, right? There are a number of tests, but because of the paucity of time, we are discussing the Durbin-Watson test, right? Here, what is the thumb value? Thumb value is 2 with a margin of 0.75, right? Means 2 plus minus 0.75. It means if the Durbin-Watson statistics lies in between 1.25 to 2.75, we say that our data has negligible autocorrelation or low autocorrelation. Right? In the same way, heteroscedasticity can also be examined. How that can be examined? By examining the residual plot. Right? Means if there is a pattern, so pattern shows heteroscedasticity. And if there is no pattern, means data is being distributed randomly, then we don't have no heteroscedasticity. There are some better tests also, but we are not discussing it because it is just an introductory class. So we are checking these assumptions in one go through the output. Meanwhile, if any question up to this point, kindly ask. If any question related to these assumptions. Otherwise, we will be moving to output. Remember, this is very important. Otherwise, the objection is the regression is actually done by the software. So what is the role of the researcher? The role of the researcher is to decide whether this is a proper technique or not. And even if this is a proper, whether assumptions are being fulfilled or not. And after that, checking the assumption, we will be interpreting the output. So this is the researcher part. That's why we are discussing in detail. So any question up to this point, or should we move forward? This is a bit technical, but it is important. So that's why I am teaching you this part. Yes, class, any question? Hello? Okay. Heteroscedasticity and homoscedasticity. Actually, the assumption is, as here, that variance of all the error term should be same. Means all the error terms should have common variance. If this is the thing, then this is known as homoscedasticity. Homo means same. But if variance of the different error terms are different, right? Means variance of a different epsilon term, different error term, different residual terms are different. Then this problem is known as heteroscedasticity. If our data has heteroscedasticity, then OLS is not that much good. So we check whether our data is having substantial amount of heteroscedasticity or not. If answer is yes, then we are not using this model. And how to rectify the autocorrelation? Okay, right? What is the remedial measures, right? We use some other method that is known as generalized least square method. So that is being not covered by autocorrelation, right? So we make a number of corrections. Sometimes we take log values, right? Like here, some perform transformation. We go for log transformation. So in a number of situation, log transformation corrects autocorrelation. Even if the autocorrelation is not been corrected, right? We use some other method that is known as generalized least square method or new way west method, right? So obviously regression is a big topic. Econometrics is a big topic. So first we introduce regression, right? If assumptions are violated, then we move forward in one step or other. So all the techniques has some corrections. Like here, multicolority. If multicolority is there, we can use principal component analysis. We can use ridge and lasso regression, right? So all these techniques can be corrected, right? But the first thing is we should recognize that there is a problem. Is it okay, Mr. Anirudh? Okay. Any other question, or should we go to the output? Hello? I know this is a bit technical, but we have to cover this. Okay. Now, this is the output. First, we are checking the normality of the residual term, first assumption. So this is the histogram. As you see the histogram, this histogram is approximately normal. As you see, this histogram is approximately normal. So we can say that our residual are following normal distribution. Further, this is the normal PP plot that I have explained earlier also while we are checking the normality. On the x-axis, we have observed value, and on the y-axis, we have estimated or the expected value as from the model. As you see, most of the points are lying very close to this 45-degree line. So through these two diagrams, we can say that residuals are following normality. So the first assumption of the normality is being fulfilled, right? So this is the first assumption. Now, the second assumption is related to autocorrelation. Right? Here we are interpreting Durbin-Watson statistics, though there are better measures also than Durbin-Watson, but just to have an elementary idea of the presence of autocorrelation. Obviously, this is a cross-sectional data, so we are not expecting the autocorrelation here. Anyway, we are interpreting Durbin-Watson. Remember what was the thumb rule? That the thumb value for the Durbin-Watson for absence or for negligible presence of autocorrelation is 2 plus minus 0.75. Means if Durbin-Watson statistics lies in between 1.25 to 2.75, you can say that the autocorrelation is negligible. So this value 1.975 is very close to 2. It lies in the interval of 1.25 to 2.75. So we can say that our data contains negligible amount of autocorrelation and there is no issue with respect to autocorrelation. So this is the assumption of independence of error terms. That is the absence of autocorrelation. Now the last assumption, right, that I have shown, that is related to heteroscedasticity. For that purpose, we will be interpreting scatter plot. Remember, we have drawn this plot by taking standardized residual on the y-axis and standardized predicted value on the x-axis, right? If there is no pattern, what possible type of pattern is? Number one, they may have a cone shape, they may have the star shape, right? Okay, as you see here, points are randomly scattered because at 0, we have point here, we have point here, we have point here, we have point here. On the y-axis, for 0, we have point here. For the x, we have point here, we have point here, we have point here. So there is no defined pattern in this data. Here values are actually randomly plotted. They are not showing a shape of the cone or shape of the star. So we can say here we don't have the problem of heteroscedasticity, right? So these three assumptions has been checked. Means in our data, Linearity is there, normality is there, there is negligible autocorrelation, there is negligible heteroscedasticity. Only one assumption has not been fulfilled, that our data has severe amount of multicolority. So as you see here, just one assumption not being fulfilled and we are getting a bad output. Bad output in what sense? If Procter and Gamble goes with this suggestion, it might be highly possible that the product would be rejected because some important predictors has been missed. Right? So these are the discussion related to all the assumptions. Now, if any question, I will be taking this first. Otherwise, we will be moving forward. So any question related to these three assumptions? I have covered these topics in a bit faster manner. Any question? Okay. So we have around 10 to 15 minutes. Already 6:50 is there. Should we start the basic introduction of the logistic regression also? And Dr. Mohsin, what you suggest? Right? Though we cannot cover them in full detail, but hello. Yes, Dr. Mohsin.
Yes, sir, we can start.
Okay, okay.
Sir, am I audible?
You are audible.
Yes, sir, we can start. We can give the introductory part.
Yes, the introduction.
Okay.
Just a moment. Let me save the PPT because it will be shared.
Okay, sir.
So now I am opening a case. And this is being shared. Rebranding of the police department. This project we did with UP Police around 3 years back. So this is a bit of real data. Okay. Now read the case. Case is there. Participant, case is there. Rebranding of the police department.
Yes, sir, it is there.
What was the objective? Police department is considering rebranding of one of its unit by altering its logo and other symbol, so to make it more people's friendly, right? So to have a better connect with the masses and give them a welcoming attitude, right? So for that purpose, they have surveyed 200 respondents through a questionnaire on the issue of perception on the rebranding, right? What is the first question they asked? They have a logo is being shown and it is being asked whether you like the logo or not, right? So there are only two options, 0 or 1. Means number one, they may like, so they will write 1. If they don't like, the 0, right? So this is a categorical variable. So overall liking is a categorical variable, and rating of these 6 perceptual variable was obtained on an extended Likert scale. The goal of the study to learn which of these 6 perceptual variable were most important in influencing the liking of the rebranded logo. These are the 6 variables, 6 predictors. Number one, departmental identity, X1, whether that logo represent the departmental identity of law and order enforcement agency. The number two is it is good looking and attractive. Number three, whether it gives the feeling of modern, vibrant police department. Whether there is no substantial change. The next one is whether it shows the emotional connect that's a part of their life and society and provide them the security feeling. And the last variable is whether it has introduced some image transformation or not. So this is the case and this is the data. Right? Data I will be showing. So before that, let us discuss this logistic regression in a bit way. So just a moment. Class, whiteboard is there? Means PPT is there?
Yes, sir. Yes.
Okay. So now in this case, that is the rebranding case, there is Y. Y means overall liking of logo. Now there are only two possible values, 0, 0 means no, and 1 means yes, right? So we can say this variable is categorical in nature or non-metric in nature. On the other side, we have these 6 perceptual variables. These are 6 perceptual variables, right? Now these variables are measurable. This is metric nature, and we are examining the dependence relationship. Right? One way dependence relationship. Now in this situation, since Y is categorical in nature, there are two tools. One is discriminant analysis. Which is based upon strict assumptions. Right? So it is very effective. But less application because assumptions may not fulfill in a number of situations. On the other side, we have logistic regression, right? Which has no as such assumptions. Right? So it is less effective, but more common applications. And related to domain wise, though I don't want to create that bifurcation, normally people of marketing and HR goes with the discriminant analysis, and people from commerce, economics, analytics, medical, health statistics, or the medical statistics go with the logistic regression. So this is our scenario. So examine the existence of the associative relationship between categorical non-metric dependent variable and several independent variable. What it does, it calculates the conditional probability of occurrence of an event. Now this is not exactly why, right? This is also known as classification problem because it classified, y is classified. If we have only two values of y, then that is known as binary logistic regression. If we have more than two values, that is known as multinomial regression. It is a very robust technique. It requires minimum of the assumption. Now, why this is known as logistic regression? Consider the value of y. Value of y can be either 0 or value of y can only be 1. These two values are possible. So if we draw a straight line, this straight line is not a good fit. Since straight line is not a good fit, so regression analysis cannot be done. So instead of the regression line, we consider this S-shaped curve. And this S-shaped curve is known as sigmoid curve or sigmoid function. This is known as sigmoid function, right? So now how it is being there? Here we consider the probability. So let me explain. Just a moment. I should have. Here, since y can take only two values, that is 1 or 0, right? And if we consider this ratio, y equals to 1 divided by y equals to 0, means this is the ratio of probability of happening versus probability of not happening. This is known as odds. Okay, this is known as odds. It is there also, right? This is odd. Py equals to 1 divided by py equals to 0. Py equals to 0 is 1 minus probability of y equals to 1, because y take only two values, right? So y equals to 0 means opposite to y equals to 1. This is known as odds. And if we take log of this odd, right? This is log of odd. And this is known as logistic function or logit. Right? So it is there. If we consider the log of odd, this is known as logistic function. So this is the logistic probability function, and here we use maximum likelihood estimation anyway. So let me explain this in a bit more manner, how the probability is used. Suppose the first column is probability, right? Obviously this p equals to 1. And the second part is odd. What is odd? This is py equals to 1 divided by 1 minus py equals to 1, right? Because p0 is actually equals to 1 minus py equals to 1. This is the either this is success or failure. So probability of failure is 1 minus success. Okay. So this is odd. And the third one is logit. Logit is log of odd. Right? Now we consider different values. So to know how the classification is done. If the probability is 0.5, if the probability is 0.5, right, probability of 1. So numerator is 0.5, denominator is also 0.5. So odd is equals to 1, right? And log of 1 would be 0. So the logit value would be 0. Now, if probability of happening is greater than 0.5, means things are happening, then the numerator is more than 0.5, denominator is less than 0.5, means this value would be less than 1. And if value is less than 1, the log would be less than 0 or negative. Sorry. If p is greater than 0.5, so numerator is greater than 0.5, denominator is less than 0.5, right? Suppose the p is 0.6, so 0.6 is in the numerator, 0.4 in the denominator. So this value is greater than 1. Since this value is greater than 1, so this logit value would be greater than 0 or positive. Right? In the same way, if this value is less than 0.5, so numerator is less than 0.5 means 0.3 for an example. So numerator is 0.3, denominator is 0.7. This value would be less than 1. So this value would be less than 0 or negative. So on this concept, it works. It's being explained here. Okay. And just I am running it to show how it is being done. Obviously, in order to interpretation, we require much of the time. Just I am showing you how it is being done. Yes, Miss Nisha, I am showing that only. We are opening another data set, that is rebranding of the police department. Okay, this is a dependent variable. So we go to analyze, then we go to regression. In the regression, we go to binary logistic. Right? We go to analyze, then we go to regression, then we go to binary logistic. This is our dependent variable. And we select all independent variable and transfer them as covariates. We are using the enter method. This is not the only method. Down here, all the predictors are significant, so we don't require the categorical independent variable. Okay. In the save, this is the probability, this is the group membership, and this is just for the demonstration purpose. In the option, we are taking Hosmer-Lomachenko test, which is used for the goodness of fit. We have the iteration history, right? And we have classification plots also, right? Then we continue, right? Style, no need to change, and bootstrap is not required. Let me check again. Categorical, not required because no of the predictor is a categorical variable. Save, done. It is just for the demonstration. In the option, we are having classification plots, right? If we want to check multicolority, we can have correlation of estimate. Otherwise, we can ignore, right? We have iteration history is there because it is showing output at all the level. We continue and then we press OK. So this is the output. Okay. So this is the output that is there. But we don't have that much time for the interpretation. So we are stopping here. That may be covered later on. Yes. So any question? These two are the big technique, very important technique. And since I have covered the conceptual part also, so that's why larger amount of time is there. So any question? Okay, I'm redoing it. Otherwise, it will be there since it is being recorded. Right. So what we do, we go to analyze, then we go to regression, then we go to binary logistic. Analyze, then regression, then binary logistic. Right. We select the dependent variable that is categorical in nature, enter into the dependent list. Then we are selecting all the independent variable from the departmental identity to image transformation, transferring them to covariates, right? If some of the predictors are categorical in nature, we are requiring dummy variable regression. So here the dummy variables are being created. Anyway, we are not covering the dummy variable. Moreover, in my data set, there is no categorical independent variable, so it is not required here. Then save. Save is just for the demonstration purpose. It is not required that you should save on your data. It is just for the teaching purpose. In the option, you can have classification plot. If you want to check the multicolority, include correlation of estimate. Hosmer-Lomachenko goodness of fit must be included, and iteration history must be included. These two things must be there. Okay. Then we continue. There is no change required in style or bootstrapping. We are not studying bootstrapping at present. And if we press OK, this is the output. Okay. Obviously, so this is again, Miss Nisha, this is a big topic, so we have to cover. Means around 45 minutes would be there. That may be covered in some other day or in some other session.
Thank you, sir, for a wonderful session. And
Sorry,
I would like,
I couldn't give much of the time to the logistic regression because already regression has taken much of the time.
yes, sir. But we will invite you soon again
No
for
issue.
this special topic. And I would like to request participants if you can give some feedback to our sir, since he has taken 3 days session and it was really amazing. If anybody is there, then who can give that feedback to our sir. and verbal, I mean, um, through their words.
Sir, good evening, sir.
Thank you.
Sir, I am Anirudh Venkatraman from the Department of Commerce. Sir, actually, I thank you a lot for making us bit clear about what is regression, logic regression, EFA, CFA, and also. We actually throwing limelights on these topics are really interesting, and the way you did it was really nice, sir. And now we are at least having some hold on the topic. And it will be useful if the organizers and the coordinator team would further extend this whole session to a offline session so that we would be able to grasp more on your knowledge. So thank you for such a wonderful session, sir.
Thank you, Mr. Anirudh.
And thank you, Anirudh.
Thank you.
Anyone, please?
That's okay, Dr. Mohsin. And thanks for all of you for. Okay.
Sir, we have some participants.
Okay.
They are interested to give some
Okay.
feedback to you, sir. So we can accept it.
Okay. No issue.
Yes.
Good evening, sir.
Good evening.
Sir, myself Jasmine Mani from Commerce Department. So actually, I would like to appreciate your dedication and effort in delivering these 3 days classes. Actually, it is really interesting. The first section regarding the introduction to SPSS, importing data, data manipulation and transformation, and yesterday's class regarding the parametric and non-parametric test, and today's section multivariate regression analysis and logistic regression analysis, especially the 5 stages, 5 steps in regression analysis. Actually, your effectively communicated with the concepts, sir. By using the real examples and in SBS also, you just explained it very clearly. So it helped us to stay focused on it. So thank you, sir. Thank you so much.
Okay. Thank you, Jasmine.
Thank you,
Thank
sir. It's a real work.
you. Okay. Thank you, Dr. Mohsin. And I will be sharing the case as well. Case has already been shared. I will be sharing the slide as well as the output. So
Yes, sir.
you people can go through that, and we
Yes,
may
sir.
take questions otherwise also through the mail or through
Yes, sir.
that can be anyway, right? So all the best to all of you. And
Okay, sir.
thank
Thank
you,
you,
DIT, for inviting me for the session. And
sir. Soon we are looking to you here in our
Okay.
university, sir. Very
Thank
soon
you.
we will invite you again.
Thank you.
Okay, sir. Thank you. Thank you. So kind of you, sir. Thank you.
Okay, bye-bye.
Okay, bye, sir.
Yes, I will send. Okay, thank you. Okay, Jasmine.